We're going to start a new unit. We're going to jump into Unit 5. Now, Unit 5 is on chemical kinetics. This is the unit that I kind of talked about a smidge earlier in the year, and I said I could really put this thing anywhere because it doesn't fit with anything else. This is the island unit, as I call it, meaning chemical kinetics is its own thing, and it doesn't directly connect very nicely to anything else we've done all year or anything else we're going to do after. Sounds strange, okay? But we're going to get started on this thing. My hope is that this is approximately a 3-week unit, okay? So keep that in mind. We have, my guess is an early February test on this one, just to kind of give you a heads up of where things are headed. We're finishing first semester, obviously. First semester is done on Thursday, I guess, technically, because Friday's conflict res. With that said, I have one more homework assignment to put in, which is Unit 4, Topic 3, which was due last Friday. I have 2 labs that I have not been grading, but I totally should be grading, that are going to get put in. Okay, there's the Gatorade lab and the solid acid titration lab that are both hanging out there as well. Those are the 3 grades missing from your gradebook currently, and then the Unit 4 test. Okay, so if you look at Infinite Campus, you can expect 4 more things to show up. If those 4 things are turned in, well then, you know, you're probably in great shape. If those 4 things aren't turned in, well then your grade's going to go that way. So just keep that in mind. We are finishing up the semester. The Unit 4 tests, I will have them graded by tomorrow. I will have a retake available tomorrow to hopefully give you a nice little window to potentially retake that before the end of the semester. Okay. Grades aren't technically due until next week, Wednesday. The semester ends this week. So I am perfectly comfortable having any of you retake Unit 4 tests through next week, Tuesday, if that makes sense. So I'll get that set up and open for you tomorrow, which will give you 6 days if you want to retake Unit 4. I think that's reasonable enough. I'm not too concerned. That feels like enough days to take care of it if you need to take care of it. Okay. And then we'll start fresh in Unit 2. All the Unit 5 stuff will go on semester 2. Sorry, did I say Unit 2? Sorry. Unit 5 stuff will go on semester 2. Okay, so all the homework assignments in this unit and everything else, obviously, will be placed there. Yes? Yeah. Yeah. I guess Tuesday will be my cutoff for late work too. In an ideal world, I don't get a mountain of it on Tuesday though. That doesn't sound great for me. That's why I was hesitant. Just being selfish for a second, but yeah, in this environment, I'll accept it on Tuesday. However, if you're on top of your late work student, meaning if you have late work but you're on top of your stuff, I greatly appreciate it. But okay, let's start 5.1. It is on reaction rates. A rate. When I say the word rate, what does that do for you? What does that mean? I'm not talking about chemistry. I'm just talking about in life. A rate. It's number, something numerical. Need to be more specific. Or could somebody elaborate on that? A frequency of something. Do you have an example of a rate in normal life? Yeah, driving a car. What is the rate of your car? Speed. What do you measure that in usually? Miles per hour. Okay. Something per something. Okay. Rate can also be related to cost too, right? I'm assuming you've heard that the term used within like buying something or purchasing something or how much does it cost per whatever, right? A rate is really just some numerical value per another numerical value. Miles per hour. It's a rate. Okay. How many, like the cost of, I don't know, apples, right? 1 apple costs this much money or whatever. That's a rate. Okay, something like that. So in chemistry, we're worried about the rate of chemical reactions, how fast chemical reactions go. Okay, and we're going to measure that by using what we call rate. Now, the units of rate or the speed or how fast the chemical reactions are going. We'll talk about in just a little bit. But this is the whole unit. Okay, the whole unit is about the speed of chemical reactions. Some of this unit's going to be doing the math of that, meaning like we're analyzing how fast the reaction is occurring using molarity and time. Okay. Another part of this unit is exploring what either speeds up chemical reactions or what slows down chemical reactions, because there's different factors that can mess with the rate. Okay. But again, this is kind of its own thing. It really is its own thing. It's chemistry. It's not like we're not doing chemistry, but the concepts in this unit are very unique compared to any other unit we do all year long. Okay. So without further ado, let's get into a little bit of this. Chemical kinetics, that's the full name, okay, because this is called kinetics. The unit is called kinetics, but that term is also used in physics, okay? So be aware, chemical kinetics is the study of how fast chemical reactions occur. Chemical reaction, well, not a good start. The rate of a chemical reaction, hold on. The rate of, okay, that one should be plural. All right, good. The rate of chemical reactions depends upon the concentration and the time. Rate is always measured in terms. Rate is always measured in terms of concentration per unit time. Highlight that, underline that, circle that, whatever. Okay? That is how we measure how fast chemical reactions occur, or how fast they are going. How is the concentration changing over the course of time? When we say concentration in this class, what are we generally talking about? When I talk about concentration, what unit are we talking about? Molarity. And that is still true, okay? For us to monitor chemical reactions and how fast they occur, we're generally going to be working in solutions or aqueous environment. So molarity is at play. Generally speaking, our rate will be measured in molarity per seconds. Molarity per minute. Okay, whatever, some unit of time. Okay? Write the balanced reaction for the combustion of hydrogen gas. See what you can do. Pretty simple reaction, I hope. We're burning hydrogen gas. So what do you need in that reaction to show them? Give you 30 seconds here, and I'll jump in. And this is not a hydrocarbon, right? There's no carbon in this one. So if you're looking to make the appropriate combustion products, be careful. Without carbon, it's tough to make CO2. What are my reactants? And when you say hydrogen and oxygen, the diatomic ones, right? Yeah, because this is elements in their pure form, but these are both diatomic elements. They're the shaded ones on your old periodic table. They must be diatomic. So I have hydrogen gas plus oxygen gas. What do I get as a product? Water gas, which is generally called water vapor, yeah. Balanced? Not so much. This isn't too bad though, I hope, right? Put a 2 there, 2 there, I think we're good. Disputes? Side commentary? I don't ask that question during A weeks, right, Jeff? You can't see me, or I can't see him. That's not an A week question. That's a B week question, because I don't get side comments. That's a compliment to you guys. And now that's been recorded for all others to hear. Okay, if I have a balloon, and I place hydrogen gas and oxygen gas in that balloon, what's going to happen? If I have hydrogen gas and oxygen gas, and I fill up a balloon, and I have both gases in the balloon, what's going to happen? It sure will. Nothing's going to happen. You're absolutely right, Luca. However, if I have that same balloon and I took a match next to it, what's going to happen? It'll blow up. And that reaction that we just wrote down will happen, right? Now, here's the deal. Okay, so let me answer my question. Sorry. Nothing. Not unless I make something happen by adding some energy, right? If I add a flame, it's going to blow up. But just because two substances are known to react with one another doesn't mean that the reaction is going to occur fast. Okay? Hydrogen and oxygen gas absolutely 100% can react with one another. However, just because they can, A, doesn't mean they will, and B, doesn't mean that it's going to happen instantaneously. Okay? The rusting of your car, right? We all live in the state of Wisconsin. Your car is over the, probably, at least 10-ish years old. Solid chance you probably got some rust somewhere on there. Okay? That is a chemical reaction that occurs. The iron in your car reacts with the oxygen in the atmosphere. Slowly but surely, it produces iron oxide, which is rust. Okay? Extremely slow reaction, right? But it happens. It happens. If you left hydrogen and oxygen in a balloon for a really long time, they'd react slowly but surely. Not at a great rate, but they'd react a little bit. Okay? Nothing much. You just get some water in there. It wouldn't be very exciting. It's more exciting to make it go fast and blow it up. Okay? Generally speaking, when you think of chemistry and you think of reactions, you think of the fast ones, right? Fire is a very fast rate of reaction. Explosions are an extremely fast rate of reaction. But there's slow ones too. Maybe those are the boring ones. But we're going to talk about both types. Most of the time, we need to talk about the slow ones in this unit because we want it to be measurable. It's hard to measure the rate of a reaction when it's like instantaneously done. That's an explosion, right? We go like from reactants to products in like a split second. Hence why all the energy is released in a split second and it blows up, right? If you have a reaction occur really slowly, you're just releasing a little bit of energy slowly over the course of time, and it's not very exciting. Anyway, okay. Look at this graph. Okay, this is a little tricky, and I'm not going to give you a ton of guidance to analyze this just yet. This is a graph of 3 different chemicals. You can look at the ketone at the bottom. I know yours is in gray, gray, and gray, so that's not wonderful. There's little shapes on there to maybe help you out, but those are really tiny too, so it's not very great. But if you look at my smartboard, if you look at the presentation on the Google Meet, you should hopefully be able to see the yellow, blue, and pink. Okay, these are 3 chemicals. On the y-axis, I have their molarity, their concentration. Okay, more specifically, not actually their molarity, but their millimolarity, meaning millimoles per liter. I've never used that term before, but you're smart people. How many milliliters are in a liter? 1,000. How many millimoles are in a mole? 1,000. Same metric conversion, right? That's just a prefix. So we'll deal with that mathematically in just a second. But we have concentration on the y-axis, and we have time in seconds on the x-axis. Okay? These 3 chemicals are changing over the course of time. What I'd like you to do is stare at this graph for a second and see if you can figure out the balanced chemical equation. That's all I'm going to say. I'll give you some time. I don't think this is necessarily easy, but you're smart people. You might be able to infer and figure out what's going on here just from the graph. Concentration versus time. Some things are going up, some things are going down. Some things go up and down by more than other things. Can you write a balanced chemical equation from the data? Go for it. I'll give you a couple minutes. If you want to talk to your neighbor, go for it. And again, when I say that, I'm not talking about at home. You can figure it out. And please talk to each other. Yes. It's a great idea. Because you might have a whole lot of nothing on your page at the moment. Is anyone moderately confident that they've approached this correctly, or anyone have a little bit of confidence that they're doing this right? No? Again, I'm just throwing this at you, right? I haven't touched a darn thing. I'm just kind of throwing some data at you and seeing what you can interpret. I heard April and Jacob were talking about up or down, right? Let's start. Go ahead. Were you gonna say something?
No.
It's okay. You can. You want to teach?
No.
Oh, that'd be fun.
If I knew what I was talking about.
I say the same thing someday. I'm kidding. God, no. Okay. Sorry, Jack, I'll stop being mean. You know I like you. I'm just, you know. If you were here, it's more fun to make fun of you. It's not as much fun when you're not here. Okay, so things are going up and things are going down. What does that tell us? Let's start there. This pink line is going down. What does that mean? Yeah, it's getting used up. You're absolutely right. Yes. These two are going up. What does that mean? They're being produced. Okay, so you're not confident, but you're absolutely right. All right. The pink line must be a reactant. Over the course of time, its concentration is going down. Well, that makes sense because as a reactant gets used up, there should be less and less and less of it. Okay. So I have NO2 on the reactant side. And as that's going down, we see two other chemical species going up in concentration, meaning they're getting made. They're being produced. Now, this isn't balanced, and I know you can totally balance it the old-fashioned way, and it's really easy, but hang with me for a second. Let's look at the graph. The pink line here, which represents NO2, nitrogen dioxide, is going down. Over the course of 400 seconds, it goes from a molarity of 10. Again, it's not molarity, right? It's like millimolarity, but for the sake of argument, it's going from a molarity of 10 to a molarity of like 3-ish. We're down by 7. If you look at the products, the blue one here, which is the nitrogen monoxide on the product side, is going from 0 to 6.9. In other words, like 7-ish. So if the pink one's going down by that value and the blue one's going up by that value, we would expect that they have the same coefficient, because however much the one is changing, the other one's changing by the exact same value. Now, in theory, we would maybe assume 1, but the problem is the other product is going up by half of what they are, or changing by half of what they are, right? So if you look at the oxygen here, the yellow line, over the course of those 400 seconds, it goes from 0 to 3.5, which is roughly, you know, half of 7. And by roughly, I mean it's exactly half of 7. So the oxygen changed by a factor of 3.5. The other two changed by a factor of, I can't do both lines, 7. So we should totally expect the coefficients to match that relationship, right? And we would make the smallest change a factor of 1, and the other one should be a factor of 2. Okay. Now, again, I know you can balance this without thinking about it like that, right? And if you look at that, that is totally balanced. But my point in showing you that is that the data is showing that same relationship that we would expect to find, just setting it up without it, right? See what I'm saying? Questions? This is a very data table-y, graphy kind of unit. which generally means negative reaction from you guys. I feel like data tables and graphs are not your friends sometimes. I don't know. You don't like making them. Let me say it that way. I think you're all pretty darn good at interpreting them. Because that's like the whole ACT nonsense, right? Literally the entirety of the ACT science section is interpreting graphs and data. Like 98% of it, then they have like one random bio question that's like, what's the powerhouse of the stuff? And then you answer it. Sound familiar? All right, cool. I teach the ACT prep course. Or I used to. I don't think I'm doing that anymore. I got fired. No, okay, let's analyze a little bit of the data. Let's go into the numbers and do some math, okay? What I have here is that the average rate of change in concentration of NO2 for the first 50 seconds is negative 4.2 times 10 to the negative fifth moles per liters times second. Prove this mathematically. What I'm doing here is we're getting a rate over the first 50 seconds for the reactant, the NO2. Okay? So the end goal is to get moles or molarity per second. Okay? That's what we want to do. Molarity per second. So if I go back to the graph and I want to solve for the first 50 seconds of this pink line, I want like the rate or the slope of that. And by the way, if you're in calculus, this unit's going to tick you off. Who's in calculus in this room in front of my face? All right, none of you are going to be mad. If you're at home and you take calculus, this is going to tick you off. Kinda. Probably have to be in true calculus to get really mad. Because if I could use calculus, this whole unit would be taught completely differently. But I can't. Because if calc was a prerequisite for this course, there'd be 2 people in it. It'd be fun, but I'd rather have like 60 of you. So, side note, if you take calc, you're not going to like this unit because we're doing not calc math when we should be doing calc math. Anyway, so I want to get the rate of that NO2 over the first 50 seconds. Molarity per second. I'm going to take my change in Y over my change in X, okay? Because my graph was concentration versus time. So if I take the change in Y of that and over the change in X, I'll get a rate. Okay, this is an average rate over that course of time. So let's go back to our graph and let's look at the pink line, because that's what I'm looking at. I'm looking at the NO2. Now, this is the region I want to get. So when I do this math, I want the final minus the initial, right? This is going to be a negative slope. That makes sense. So our value should totally be negative. I'm going to take 7.9 minus 10. Okay, I don't think there's more sig figs, but we'll leave it like that for now. This is going to be divided by my change in X. X is time. Where I want to end this is 50 seconds, and where I started is 0. So I'll have 50 minus 0. And when I punch all that in, that means you. Or me, I suppose. Hopefully you. What do I get? I go 0.042. What's the label on that feller? You go back to the graph. What are we? What's my units? Say that again. We're missing one thing, but that's what I said. Millimoles per. What? Read the y-axis one more time. Correct. Millimoles divided by liters, technically times seconds on the denominator, right? Or like that whole term over seconds. So I have millimoles divided by liters times seconds. Is that what it asked me to do? No, it wants moles. Okay, how do I turn a millimole into a mole? Well, let me just do this whole thing factor label style just for fun. I like the liters and the seconds chunk, right? I don't want to mess with that because that's what I have in the denominator for the actual number we were supposed to compare it to. I just want to switch my millimoles into moles. How many millimoles are in a mole? 1,000, right? That prefix still applies just like it would for millimeters or milligrams or millimeters. Okay, we don't measure distance in chemistry very often, but still works. Same prefix. Divide that by 1,000. Hey, we get the same thing. Okay. So every now and then we have weird units in this lab, or in this unit as well. Okay, the units get funky sometimes. Because sometimes we need the scale to be like friendly. So we'll use millimoles or we'll use something that's not traditional metric units. All right, so since the concentration of NO2 decreases with time, right? This is the reactant. So if I go back, here is my molarity of NO2, which is my reactant. Over the course of time, its molarity goes down. Right? No disputes? Okay, so since this decreases with time, any rate expression, meaning when we express what the rate is for a chemical reaction, if we use the reactant, it's going to be a negative value. See what I'm saying, right? We literally just did this. What we did in the previous chunk is we solved for the rate of change for NO2 over the first 50 seconds of this reaction. It went from a molarity of 10 to 7.9. And as a result of that, if I calculate the rate of change over those 50 seconds, I get a negative rate. I got negative 4.2 times 10 to the negative fifth moles per liter times second. Okay. Now, chemists don't like negative numbers. So they flipped the sign. Okay. The next sentence here is, when analyzing the rates of chemical reactions, we almost always reference reactants. I almost want to make that a stronger sentence and say we always reference reactants. Okay. So rate of chemical reaction, we always reference reactants. Okay. When we talk about how fast a chemical reaction is occurring, we will always, I don't know if it's true, but 19 times out of 20, we're going to be looking at the reactants to analyze the rate. How did the reactant change? Okay. The products are there, and there's some times where it's appropriate to look at how fast the products are produced. But generally speaking, if we want to analyze how fast the chemical reaction is going, we look at the reactants. Now, as a result of that, chemists like positive numbers. So, generally speaking, we're going to turn those negative rates for the reactants into positive values. If you look down here, I have the rate of this chemical reaction can equal one of three things. The rate of the chemical reaction that we just looked at can either be the change in the reactant over the change in time, flipping the symbol. Or, ignoring this first term, right? The rate of the chemical reaction, this one, could be measured in the change in this product over the change in time. That would also work. Or, ignoring the first two terms, the rate of this chemical reaction could also be measured in terms of 2 times the change of oxygen divided by the change in time. Why does this rate, if I was to use this change for this reaction, why would I need to double that rate? This gets confusing. It totally does. But do you notice how my coefficients and my rates are like inverse of what they or like the opposite of what you want them to be? See that? Like if I measure the rate based off of this reactant, it's like a coefficient of 1. You could think of it as almost. If I measure the rate off of that product, it's like a coefficient of 1. But if I measure the rate off of the other product, I need a 2. Do you see why? Because I need, these three terms are all equal, right? That's why there's equal signs there. Sorry for taking your brains for a loop here. Let me say it a different way. When this reaction happens, I make both of these, right? Which one do I make faster? Which one do I make more of? That one. Why? Uh-huh. So when this reaction goes, and I'm making products, I make 2 nitrogen monoxides for every 1 oxygen. So if I want to compare the rate and make it equal, this is going twice as fast as that. Right? So if I want to make the rate of those 2 things equivalent, I would need to double the slower one. Good news, we won't look at that too often. That's really not a big part of this unit, is like analyzing or comparing rates within a chemical reaction. Generally speaking, the only one we care about is that guy. All right? Generally speaking, when we do problems, all we really are going to look at is the reactant. 19 times out of 20. Hence why I said almost always. The one big takeaway from this slide is when we do analyze the rate using reactants, we flip the sign to make it positive. So the normal way of doing math with a reactant would give us a negative value because the molarity is going down, but chemists flip that sign to express the rate. They describe the rate in positive terms. All right, that leads us to something else. There's a mathematical expression that shows how the rate depends upon the molarity of the reactants. Here's the deal. The rate of a chemical reaction can change during the reaction. Okay? Do you see how this is curved? Okay? What that's trying to tell you is that the rate isn't consistent throughout. The rate is literally changing as the reaction goes faster or progresses. That leads to problems. Okay? These aren't linear graphs most often. It's rare to see a linear graph where the concentration is changing over time. They exist, but they're very rare. Okay, so we need an equation to help us out with this. This equation is called the rate law. The rate law includes a couple of things. First, rate, which is molarity per second. All right, this guy right here. Molarity per second. Or like we did in the previous couple slides, right? We did moles per liter times seconds. Doesn't matter which. But that's rate. Okay, that's how we express how fast the chemical reaction is going. How is the molarity changing over the course of time? The next part of this, rate equals K, little k. This is known as the rate constant. All right. Times, brackets, capital R. What do brackets mean in chemistry? When you see something in brackets in chemistry, do you remember what that means? I'll take your silence as a no. If something is in brackets, that's its molarity, okay, or the molarity of that stuff. Okay. So for example, if I were to say like the molarity of H1 plus, or if I bracket out H1 plus, what I'm really looking for there is the molarity of H1 plus, okay? Whatever that number might be. So brackets mean molarity of a substance. So I have the rate of a chemical reaction equals the rate constant, we'll talk about that feller a little bit more later, multiplied by the molarity of a reactant. Capital R is just a placeholder for some chemical reactant. Depends upon what reaction we're looking at. The last part here is the exponent. N, little n, that's called the order of a reaction. Okay? This is basically determining the curvature of your graph. Some are more curvy than others. Okay? They have a higher order. Sorry. Random students walking by waving. And by random, I mean Eric Schmidt. That was an audible response. We're familiar with Eric Schmidt. Excellent. I'll leave it at that. Okay, so a couple things. With this rate law, in an actual chemical setting, in a lab, okay, these, both the rate constant and the order, K and N in this expression, must be determined by actual experimentation. These are not things you can look up. I can't go to a chemistry book and find the rate constant for a chemical reaction. It's not going to be there because the rate constant depends upon a lot of things. What's the temperature? What's the pressure? What's the molarity of the concentration or the reactants? Okay, there's a lot of variables that go in that value. So as a result, it's not something that's in your packet. It's not something you can go find. It's something that must be provided through data. Similarly, N, which is the order of the reaction. And I'll explain what the order is in the next couple slides after this. That is also not something you can look up. We must have data to figure it out. Okay? We're going to use this expression quite a bit. It's not that complicated, I promise. But the key takeaway is that's a reactant. This and that, the rate constant and the order, must be determined through data, an actual experiment that somebody actually did. Cannot look them up. So when we do the math, those values must come from data, not from a book or your packet. Okay. How we doing? It's like the same stuff I taught you last week, isn't it? It's like it's a completely different class. I know. I'll give you some honesty. This was my least favorite topic when I learned chemistry. I don't mind it now, but when I learned it, I'm like, oh, kinetics is dumb. So if you feel the same, I won't take it personally. I understand. Yeah. Let's do some problems. What we're going to do over the next, I don't know, 4, 5, 6, whatever problems I have in there, is something called the method of initial rates. Okay. We're going to use the method of initial rates. It's a problem-solving kind of process. We're going to use this method to determine the rate law. The rate law is this thing, that equation. Okay. So we're going to use some method to figure out this equation for random reactions, basically. All the reactions I'm going to give you in the rest of this sheet are generic. They're not real things. Okay? Because real things usually don't behave as nicely as fake made up things. So we'll use some fake made up things. Okay. All right. So here's a little data table. In this data table, some chemist ran 2 trials. And what was happening is they had a reactant A. And that reactant A was reactive. Okay, really exciting stuff so far. And what they were able to do is they were able to determine the initial rate of the chemical reaction, or how fast the reaction was going at the very beginning. That's what the word initially means. Okay? So from this data, we can or should be able to write out this expression. That's the end goal. The end goal is to take that data, this stuff, and end up with an equation that actually makes sense. Sound good? So how do we do that? Looking at trials 1 and 2, how did the molarity of A get changed? From trial 1 to trial 2, what did this experimenter do to the molarity of A? Sure, can I use a multiple instead, or like a multiplication factor? So what do they do from here to here? They tripled it, yes. They multiplied it by 3. So from trial 1 to trial 2, the experimenter tripled that molarity. I'm going to put times 3. What happened to the rate from trial 1 to trial 2? It increased by a factor of 3. Now, here's the deal. Using this method of initial rates, what chemists are doing is they run a couple trials and they mess with the molarity. Okay? That's the independent variable in this experiment. The chemist is changing the molarity based off of whatever they want it to be. So from trial 1 to trial 2, this chemist tripled the molarity. And then they collect data on how fast the reaction's going. So the concentration tripled. What happened to the rate? It also tripled. Okay, that relationship of how when you change this molarity, how that messes with the rate, that's going to help us determine the rate law. Okay, so what's the difference? Times 3. Hold on. Suppose I can answer down here too. Sure. If the rate increases by the same factor as the molarity, the rate is what's called first order in terms of that reactant. Okay, the language is getting a little annoying. I understand that. Okay, let me read that again. If the rate increases by the same factor as the molarity, that is said to be a first order reaction. Now what that does is it gives us a rate law that looks like this. I'm going to put a 1 right there. Okay. The exponent in this equation is known as the order. Okay. This relationship between how the molarity was changed and in turn how the rate changed is known as the order. This was a first order. The little n, the little exponent, is where that number goes. If it's first order, you put a 1. If it's fourth order, you put a 4. If it's sixth order, you put a... Excellent. You guys are just... Good work. That's solid stuff. Okay. So from this data, it was determined that the order was first because the relationship between this change and this change were the exact same. Okay. Let's look at another one. In this one, we now have the reactant W, which isn't tungsten, by the way. I'm sorry. It's just like a placeholder because there is an actual element with the symbol W. Wherever it is, 74. Okay. So don't let that throw you off. This is not tungsten. Doesn't matter, I guess. But anyway, looking at trial 1 to 2, what did this person do to the molarity of the reactant? They doubled it. Okay. What happened to the rate? It quadrupled. Now, I want you to write this a very specific way. Okay? This doubled. The rate quadrupled. I know you know that. That's fine. But I want to write this like this. Okay? The reason why I want to write that change as 2 squared is because that squared part is my order. That determines the little n in my equation, in my rate law. Okay? So here's how I say this, and this is really, really important. Okay? If W increases by, if W increases by a factor of 2, the rate will increase by the exact same factor raised to some power. Here's the deal. In all of these problems, in all of these little data tables that we're going to look at over the end of the class today and the start of the class tomorrow, however you mess with the molarity, this rate will change by that exact same factor raised to some power every single time. So in other words, what I want you to get in the habit of doing, and I'll just mimic it right now before we try another one. The habit is this. How did that change? Okay, that doubled. What that means is this is also going to go up by that same factor. What's the exponent need to be to make that true? In this instance, that exponent needs to be 2, right? Because it's quadruple. But I don't want you to write it times 4 right there, because that makes things a smidge more confusing. And the reason why that makes things a smidge more confusing is because that squared part is telling us that this is second order. The order is the exponent. When we find the relationship between the change in molarity and the change in rate, the exponent of that relationship is the order of the reaction. And that's what helps us determine the actual equation. Okay, so in this instance, rate equals K. We haven't solved for that yet. Put a pin in it. Okay, we'll figure that out tomorrow. Rate equals the rate constant multiplied by the concentration of whatever the heck I was looking at, which is W, raised to the power of the relationship between this and this change, the change of concentration compared to the change of rate. This is a weird lesson to teach. And every year I teach it, I feel the same. I can't tell if you're bored or if you're confused. That's the hard part with this lesson. And I think it's sometimes both. You're so confused, you've reached boredom. Or you're so bored, you've stopped paying attention, now you're confused. It's a circular situation, I think. Take a look at this one. Let's do one more before we run away. Now, this one, the chemist went backwards on what I've shown you the previous two. But here's the cool thing. These trials are completely independent. Meaning, does it really matter that I call this trial 1 and I call this trial 2? No. Who cares? Okay? The reason why I say that is because I could totally look at this and be like, okay, from trial 1 to trial 2, it got cut in half. And that's fine, but it's kind of annoying. I'd rather work in like positive integers, not like decimals and fractions and stuff, or dividing, right? I don't really want to use division either. So what I'm going to do is I'm always going to go with an increase in my molarity, because it just keeps the numbers friendly. So that's great that this is trial 1. That's great that that's trial 2, but they're independent. I don't care which one comes first or which one's called what. I'm just looking at the relationship between those two trials. So I'm going to say from trial 2 to trial 1, that increased by a factor of 2. Now, without even thinking, I'm going to write this. Because, however the molarity changes, the rate must change by the exact same factor raised to a power. Now, what's that power in this instance? 3, because 2 cubed is 8. Correct. So you're bored. Okay, good. I'd rather have you be bored than confused, I think. I don't know. I don't like either of them, I guess. I don't know. Philosophical issue. Wrong board. So if the concentration increases by a factor of 2, the rate will increase by the exact same factor raised to some power. In this example, the rate increased by a factor of 2 cubed. So the rate is what order? Third, exactly. That's all it is, right? Okay. And the overall rate law would look like rate equals K times the molarity of G, whatever the heck we got, raised to the third power. We have done no math, really, I guess, right? We haven't used this equation for any mathematical purpose yet. All we're doing is interpreting data to set that up. Tomorrow we'll actually do some math with it. Okay? That's all I got for today. If you're at home, have a lovely evening. If you're in front of my face, grab a sanitizing wipe and easy. It wasn't that bad. Not saying it was great, but